Thank you. Thanks a lot for the invitation. It's great to be here. I am going to speak about recent work, fairly high level. This is going to be. I hope it's not gonna be too fluffy. We'll see. I guess AI is changing the world, right? It's going to bring world peace. There's no need to explain why deep learning is important. It's basically all over the place. It's so, I think, it's so common that the term deep learning is kind of becoming outdated because it's implicit in AI, right? All the modern AI, it's all around deep learning. And there is a dark secret to this technology, which is maybe not so much a secret for the crowd here, and that is that we don't really understand what's going on sufficiently well. We don't know why these algorithms work the way they do and what makes one better than the other. And it is important, not just because of scientific curiosity, but also because maybe it'll make the algorithms work better. And even if it doesn't, there are domains in which we're not going to let algorithms that we don't understand operate and make decisions, right? Critical domains like healthcare or other things. And over there, we might block the progress of AI until we have a better understanding. So while it might not always seem this way with ChatGPT and all the developments in the consumer world, I firmly believe that theory is necessary for AI to start proliferating in other domains that are more critical. So yes, we're all convinced that theory of deep learning is important. And what I'm going to do in the next 10 minutes or so is kind of a little bit of philosophy, kind of my own perspective on the landscape of deep learning theory, what the main questions are, and then we're going to dive into a specific question and talk about some actual results. Okay, so if we want to talk about deep learning, we have to start with statistical machine learning, because at the end of the day, deep learning is a special case. And the most basic statistical learning setup is supervised learning, and it operates as follows. We have some instance space. Okay, this is the set of objects that we want to infer something about. Okay? Set of images or text sequences or whatever. And there's some label space. Okay, the set of possible labels that we could assign to instances. So it could be cat or dog if we're classifying an image as a cat or a dog, or it could be some continuous number. Could be anything. It could also be a translation of text in Italian to text in English. So the possible labels of the texts in English. There is some distribution over labeled instances. We don't know this distribution, but we do assume that it exists. And there's some loss function that, given two labels, returns a non-negative number that indicates the extent to which they deviate from one another. And the basic task in supervised statistics is as follows. We're given a training set S, that's a set of pairs of instances and labels. It's drawn IID from the world's distribution. And given that set, we want to return a predictor. That's just a function that intakes an instance and returns a label. And we want that predictor to minimize the population loss. Okay? Population loss, that is the average loss, the average discrepancy between the true label and the prediction when the labeled instances are distributed according to the world. So we want to minimize this thing. It's not easy. In fact, we can't even measure this thing because we don't know D. And if you sweep away a lot of the details, then ultimately what we do is the following. We predetermine a class of predictors. Okay, sometimes it's called a hypothesis space. And then, given the training data, we return the predictor within the class that minimizes the empirical loss. This is, again, the average loss, average discrepancy between true label and prediction. But now the average is over the training set. Okay, so this is all well known, I assume. And at the end of the day, we care about the population loss of the predictor that we return, and it's governed by three factors. You can see here in this illustration, the external box, that's the set of all functions, has nothing to do with us. And the internal one, that's the class of predictors that we fixed in advance. F star D, that is the optimal function, okay, the optimal classification function, if you will. It's a property of the world. H star D. That is the optimal predictor within our class. So it exists, but we can't find it because we don't know D. What we can find theoretically is H star S, which is the predictor that does the best job in the training set. Numerically, sometimes it's not easy to find H star S, or sometimes it's not possible, and we return some approximation H bar. And we care about the population loss of H bar, and it's governed by three factors. The first, approximation error, also known as expressiveness. This is a representational source of error, right? Results from the fact that our class predictors might not be able to fit the world's distribution. The second factor is statistical. That's generalization, estimation error. This results from the fact that the training set's finite, right? If it were infinite, then fitting the training set would mean you're doing a good job in the real world, but in practice, you might overfit. And the last source of error is, again, numerical. It's due to the optimization process not necessarily fitting the training data in the best possible way. So there's another source of error here. And at its core, statistical learning theory is about these factors and how they trade off with one another. In classical machine learning, which isn't exactly well defined, but we could think of linear predictors, the situation is fairly well understood. The empirical loss minimization, the objective in fitting the training data is usually convex, and there's just one minimizer, and we can find it pretty much efficiently in reasonable time. And for the expressiveness and generalization, we have the well-known bias variance trade-off, which roughly speaking means that if you make your predictor class larger, obviously the approximation error is going to go down, but you are more prone to overfitting. So you might suffer from the estimation error, and vice versa. If you shrink the predictor class, the approximation error goes up. You can represent less, but you're less prone to overfitting. And there's some trade-off here and a sweet spot, usually somewhere in the middle. Overall, many would say that we have a fairly well-developed theory for what's going on there. In deep learning, situation is very different. The predictor classes are neural networks, which, for me at least, the broadest definition are compositions of parametric transformations, typically nonlinear ones, and there's an entire zoo of neural networks that everybody knows. And there, the situation is very, very different. Okay? It starts off from the empirical loss minimization problem being a non-convex program. Okay? And so there isn't just one minimizer. There isn't just one predictor that best fits the training data. There are a lot of them. Okay? And for some miraculous reason that we don't fully understand, gradient descent somehow reaches one of these predictors, one of the predictors that fits the training data optimally. And I say that because it reaches training error of close to zero in many cases. And for expressiveness and generalization, there's a vast difference from classical ML. It's even more peculiar. We know pretty much for a fact that some predictors that fit the training data generalize and some don't. And with natural data, I guess the data that deep learning works for, it is very often the case that the predictor returned by gradient descent generalizes well. And maybe most surprisingly is that if you take your predictor class and you make it larger, obviously the approximation error goes down. In many cases, the estimation error goes down as well. So larger models oftentimes generalize better. This seems to defy the bias variance trade-off or the no free lunch theorem. For those that know, you can kind of eat the cake and keep it full. Right? You work with a larger model, you can represent more, and somehow you generalize better. And we don't fully understand what's going on here. Okay? Hence the reason for workshops like this. All right, so that was a little bit of philosophy. And now we're going to dive into a question of generalization. Okay. This is going to be based on a recent paper that's going to appear in the upcoming NeurIPS, and I'll also, I guess, refer to an ancient work from prehistoric times, 2019, that was done in Princeton, with Sanjeev Arora and then some of the students. That was in the postdoc days, and this recent work is with my PhD students, Yotam Alexander, Yoni Stutsky, and Yuval Ran Milo. Okay, so let's dive a little bit deeper into the question of generalization. Right? So, as I said, classically, we understand generalization through the bias variance trade-off. Okay, so you can, there's this famous illustration, right? You're trying to fit a curve to these points. The instance space here is the reals, and so is the label space, and the predictor classes are polynomials. If I restrict myself to work with polynomials of degree 1, like linear affine functions, then I'm going to underfit. I'm not going to be able to fit the training data. If I work with polynomials of very high degree, I can fit the training data perfectly, but this is a way to fit the training data that doesn't seem to make sense, right? We don't really believe that these fluctuations are real. And in between, there's some sweet spot. And the trade-off, if you want to control this, then it's either by limiting the model size, in the polynomial case, it's the degree, or you could also add regularization. Right? Deep learning, neural networks that are trained with gradient descent often generalize well, despite having a size that's way bigger than the training set, right? They're highly over-parameterized, and there is no explicit regularization. In this regime, there are overfitting solutions. Okay? So we take a neural network with a lot more parameters in training than training examples, and somehow gradient descent returns some kind of function that behaves nicely and generalizes. Okay? And the question is, why does this happen? So there are different views on this question. There's one which has become kind of conventional wisdom. I think many people had different works on this, and I did too. And the conventional wisdom is that there's some implicit bias. Okay? There is, as I said, not all solutions fitting the training data generalize. Some do, some don't. And there is something special about gradient descent. Gradient descent somehow tends to fit the training data in a way that does not overfit when the data distribution is natural. And that's the view that's become very common by now. It started, I guess, one of the early works was from Nati Slebo and his group from Chicago, TTI, and it's become kind of conventional wisdom. And a couple of years ago, an alternative view was proposed. And under this view, it's called the volume hypothesis, most of the predictors fitting the training data generalize well, and gradient descent, all it does is fit the training data in a non-adversarial way. So it's not too terrible. But other than that, all it does is just fit the training data. So basically, any reasonable way to fit the training data is very likely to give you a solution that generalizes. Okay, so under both views, gradient descent returns a generalizing solution, and there exist non-generalizing solutions. But philosophically, these views are very, very different. One of them, the first, assigns very special properties to gradient descent and views gradient descent as a source of a lot of the magic. And the second view says that it's much more about the data and the architecture, and all gradient descent does is fit the training data in a way that isn't terrible. So since the kind of introduction of this view, or since it became popular, maybe about 2 years ago, there have been works that have tried to confirm it. And there have also been works on implicit bias. I don't know if you can see the gray here. These are some citations, but basically there have been many works over the years that show that gradient descent yields good generalization. And a lot of these analyses critically rely on specific properties of gradient descent, which seems to support the first view. But then on the other hand, recently, it has been shown that the volume hypothesis holds in various settings involving wide networks and deep networks. Okay. And there has been pretty much, I think, one work that actually showed a negative result on the volume hypothesis, showing that for wide networks, actually it doesn't seem to hold, and yet gradient descent still yields generalizing solutions. Okay. So overall, there seems to be conflicting evidence, and the situation is still unclear. Okay. Now, what I'm going to talk about is a theoretical testbed, matrix factorization. I'm going to present it, and then we're going to analyze what goes on there. Okay, so this is going to be our purpose today. Try and get an answer of whether the generalization stems from gradient descent or not for a theoretical testbed. Okay, so we're going to look at the problem of matrix sensing. Okay. This is super basic and fundamental problem in science and engineering. It appears in various contexts. And the task is as follows. I have a low rank ground truth matrix W star, okay, M by M prime, and given linear measurements, okay, Yi, I'm given linear measurements that correspond to measurement matrices Ai. Okay, so I get these numbers in these matrices. And I know that these numbers, Yi, was generated through the inner product between the corresponding matrix and the ground truth. Okay? And this is interesting when I have less than M times M prime measurements. So I don't know what W star is. I have more variables than equations, but I do know something about W star. Otherwise, you can't do anything. And what I know is that it is low rank. Matrix completion, that's a special case that's been looked at a lot. And here, basically, the measurement matrices are one-hot matrices, which means that I observe entries. Okay? So I see entries from a matrix, and then there's this kind of Netflix prize that Netflix had of trying to predict how much different people are going to like different movies. Right? You get ratings from different people on different movies that they saw, and it's a very kind of sparse set of entries that you have values for. And then if I can infer unseen values, I can tell how much people are going to like movies that they didn't see, and then hopefully advertise and make money off of this. Okay, so that was the prize, and it's pretty old by now, but at the time, the method that gave the best results was that the ground truth is low rank. Okay? And low rank data comes up in various settings in natural ways. Okay, so the training loss for us in matrix sensing is going to be the mean squared error over the measurement matrices AI. Okay? So I just take an average of the squared error between the linear projection of the ground truth and the linear projection of the solution that I'm evaluating. Okay, W, that's the solution, and I can compute its train error this way. And the generalization loss is similar, but now you don't take an average over the measurement matrices, you take an average over matrices that are outside of the training set, and more specifically, orthogonal to the training set. Okay, so B is some orthogonal space, orthogonal basis for the space that is orthogonal. Okay, it's a basis for the space that is orthogonal to the one spanned by the measurement matrices. Okay, everything's simple so far. And matrix factorization, this is something that's a very common testbed in deep learning theory. And it boils down to solving matrix sensing using a simple model. And this model is a parametrization of the matrix you're looking for as a product of matrices. And in some cases, you also allow pointwise nonlinearity in between. And we're going to look at this more general case. Okay, so I'm trying to solve low-rank matrix sensing, and I'm representing the solution W in this way. If the nonlinearities don't exist, or the identity, it's just a product of matrices. Okay, and you should think of the case where the dimensions, the hidden dimensions here are large. So I'm not restricting the rank in any way. And it's pretty clear that this is analogous to fully connected neural networks, right? This matrix factorization. We are going to look at two training algorithms. Okay. The first is gradient descent, right? Which means to initialize the factor matrices near zero, and then update each of them using the gradient of the training. And there's some learning rate eta. This is all standard, nothing special here. The second algorithm we're going to look at is guess and check. It's a theoretical algorithm. It's not something you actually run. And what it means is the following. Given a distribution over the parameter matrices, W1 to WL, and given some threshold epsilon, okay, I sample from the distribution, just sample again and again and again until I happen to be lucky, or maybe it's not lucky because I continued until I happen, and I get that the training loss is smaller than epsilon train. I'm just guessing, 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 and checking, 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 guessing and checking, guessing, checking, and stopping when I reached low training. And this is equivalent to drawing from the conditional distribution, meaning to drawing from P conditioned on the training loss being low. Okay? And you can think of this distribution as inducing some kind of measure or inducing a volume. And then the volume hypothesis can simply be stated as guess and check generalizing well. Okay, so if the parameters, if every entry in every WI is bounded between -1 and 1, I can think of the uniform measure. Okay, P could be the uniform measure. And then I'm just uniformly sampling parameters, and the probability that I generalize, given that the training set is low, you can actually define it to be the volume, the relative volume of generalizing solutions within the solutions that fit the training set. Okay, so this is guess and check. So we have two algorithms, gradient descent and guess and check. Let's talk a little bit about gradient descent, which is something that's been looked at a lot. And there have been a lot of works on the implicit bias of gradient descent. We're hearing some today, and specifically in the context of matrix factorization, there have also been a lot of works. And I'll give some intuition. This is the work that we did in 2019. It's a dynamical analysis, trying to give some intuition as to why gradient descent leads to good generalization of matrix sensing. So if we let sigma r be the singular values of the product matrix, this original work was for linear matrix factorization, meaning no nonlinearities. It was then extended, but I'm showing this here. It can be shown that gradient descent with small initialization and small learning rate roughly leads the singular values to move at a rate that is proportional to their size exponentiated by something. Okay? That something depends on the depth of the matrix factorization. And then, again, roughly speaking, this would mean that if you initialize close to zero, then the singular values initially move slowly because the rate is proportional to something small. And then every singular value, once it reaches some critical threshold, then it starts moving quickly. And this induces an incremental learning phenomenon. This is an empirical. You can see the iterations in the x-axis and the singular values in the y-axis. And it starts off near zero, and you can see kind of the singular values shooting up one by one. And basically, this incremental learning leads to low rank. And so this is an early analysis that was then extended and used by various works to prove convergence to low rank solutions. And just as a side note, this actually found a practical application. It's one of the only techniques that I'm aware of in practice that are actually inspired by theory. Usually theory lags behind. And the idea there is to take a neural network, a standard kind of state-of-the-art one, and just take a parameter matrix and parameterize it by a product of matrices. Just turn a matrix located in some layer of a neural network, turn it into a matrix factorization, run gradient descent, and you get this kind of implicit rank minimization. And then you can compress the layer, so you can basically decrease the size of your neural network, and it sometimes also improves generalization. And it's kind of a handful of works that made use of this technique. Okay, so now we are interested in guess and check. Okay? If we manage to show that guess and check leads to good generalization, it kind of means that despite all the analyses around special properties of gradient descent, in fact, these special properties are not necessarily needed, because something as naive as just randomly choosing weights and waiting until they fit the training data, something that naive gives you good generalization too. So the core, the crux of the generalization is not the special properties of gradient descent. Okay, that would be the case if we show that guess and check indeed gives good generalization. We're going to split the analysis to two cases, one for wide matrix factorizations and one for deep matrix factorizations. Wide means that the hidden dimensions of the factorization are large. Deep means that there are many matrices. Okay. So for wide matrix factorization, what do we show? Well, here's a theorem. We have epsilon train and epsilon generalization. And this theorem applies to a case where the activation is anti-symmetric. Doesn't need to be linear, but it is anti-symmetric. So tan H would be maybe a common example. And then we can show that under mild conditions, if the hidden width is large enough, and it doesn't need to be, it's polynomially large, then you get this bound. What does this mean? Let's parse this. So what do we have here? This is the probability that the generalization loss is less than epsilon generalization. And here we just draw W from the distribution P while ignoring the training set completely. So basically, this would be the probability of generalizing if you just draw a matrix, you just sample a matrix and completely disregard the training set. On the left here, this is the probability of generalizing conditioned on fitting the training data. Okay? And what this bound tells us is that the difference between these two things is small and gets smaller the wider the network is. So if my network is wide, then the generalization of guess and check is no better than just sampling a random solution while completely ignoring the training data. Okay. So basically, this means that guess and check entirely fails as the width grows. Okay. So it's just a few words about the proof of this thing. I'm going to keep it very high level. So you can show that the columns of the matrix W, this is the matrix that we factorize, they can be thought of as the outputs of a neural network when the inputs are standard basis vectors. And then use kind of the results tying neural networks to Gaussian processes, and then show that as the width grows, the factorized matrix converges in distribution to a matrix WIID. And as the name of this matrix would suggest, its entries are identically and independently distributed by just the standard Gaussian. Okay, so as K grows, the factorized matrix becomes closer and closer to a matrix with independent entries. And because the measurement matrices are orthogonal to the matrices defining the generalization loss, because of that, the events of low training error and low generalization error are independent. And that means that if you condition on this event, then the probability of this event doesn't really change. Okay. So W is close to WIID, where conditioning on low training loss doesn't say anything about low generalization loss. And you can bound the distance between W and WIID, and that will give you a bound on the distance between these events when WIID is replaced by W, which is what you see here. Okay. So this is not that important, the proof sketch. Bottom line is that for wide matrix factorization, guess and check is no better than just guess. Okay? Just guessing, drawing from the prior and looking at the generalization loss. For gradient descent, there are results that specifically apply to this setting. And basically they show that as long as the width is larger than the dimensions of the factorized matrix, gradient descent generalizes well. So this is a case, a very fundamental and basic one, where guess and check fails and gradient descent succeeds. Okay. And to my knowledge, this is the first proof of a standard or a well-studied problem where gradient descent generalizes well, while guess and check does not. Okay. So in this case, the volume hypothesis does not hold. And yet gradient descent generalizes. So I would say the situation looks more like the picture on the left. Okay, and again, this is the first result that I'm aware of that shows this. Most of the analyses of the volume hypothesis with guess and check, their stated goal is to show that the volume hypothesis holds, and they show it in various settings. We have here a negative result in the standard setting. Right? This happens empirically. Okay? In these plots, what you can see is x-axis, that's the width of the factorization. Y-axis, that's the generalization loss. And you can see the generalization attained by gradient descent, and for pretty much all the widths, it gives good generalization. Green, that's the prior, the generalization of the prior, meaning the generalization that I get if I ignore the training loss. I just draw a matrix, check its generalization loss. And blue, that's what guess and check gives you. So you can see that as the width grows, and it doesn't need to be very large, the blue approaches the green. So the generalization attained by guess and check becomes trivial. This is for linear activation. This is for tan-H. The theory covers both. And it also happens with other activations that the theory doesn't apply to. And this would be with leaky ruddy in this case. All right, moving on to deep, the deep case. Here, the situation is very different. But So here's the result that we show. You have epsilon train and epsilon generalization. Assume that the ground truth, this result applies to a specific case, a case where the ground truth has rank 1 and the activation is linear. We almost extend this to higher ranks. There's some missing part in the proof. So this is the end-to-end theorem that we have is for rank 1. Then you can show that under pretty mild conditions, there exists some constant C, a universal constant, such that for any depth D, any number of layers in the factorization, the probability of generalizing, okay, given that you fit the training set, is high. Okay? More specifically, given that the training loss is smaller than epsilon train, the probability of the generalization loss being smaller than C times epsilon train is high. Okay, what do I mean high? It's 1 minus 1 over D. Okay. So in this case, where I fix the width and take the depth to be larger and larger, guess and check does generalize. And I don't really need gradient descent for good generalization. Almost any reasonable algorithm that fits the training loss will generalize, even one as simple as guess and check. Okay? So in this case, the volume hypothesis does hold. A few words about the proof of this result. So you can express the factorized matrix. Recall that the activations here are linear, so you can express it in this way. I just have the first matrix on the left, the last matrix on the right, and in between I have L minus 2. L minus 2, or D. I'm sorry, this notation problem here. L and D are the same. So it's D minus 2 matrices multiplied by one another. And then I could use known bounds on the spectrum, singular values of products of Gaussian matrices, to show that this matrix in the middle, the L minus 2, the product of L minus 2 matrices, is close to a rank 1 matrix with high probability. It's with a probability that decays exponentially fast in depth. And the same holds for the matrix W, meaning that if this one is very close to rank 1, I multiply by the left from a random matrix and from the right by a random matrix. I don't change the proximity to rank 1. Okay. And under a relatively mild assumption on the measurement matrices, it's an RIP style assumption, the event of having low training loss, okay, and high generalization loss, the probability of these events holding jointly is low. Okay. So I have a matrix W, it's close to rank 1. And basically this means that if the training loss is low, the probability of this matrix being far from the ground truth is low. Right? So this matrix will achieve low generalization loss. It's not going to achieve high generalization loss. And then because the probability of fitting the training data is bounded from below, then we can use the definition of conditional probability and get that the probability of generalizing, given that the training loss is low, is high. Okay. That's the basic idea here. We show empirical demonstrations. This is what you get when you take the theoretically analyzed setting. As the depth increases, the generalization loss of guess and check goes down, and the generalization loss of gradient descent is good throughout. And the phenomenon extends also to settings beyond our theory, like the 10H and other activations. All right, so I guess I'll conclude. So start with a recap. Understanding deep learning requires addressing three fundamental questions: expressiveness, optimization, and generalization. And for generalization, there are two competing hypotheses. Implicit bias, which states that among the predictors that fit the training set, those that generalize well are special, and somehow gradient descent finds one. That's the more conventional view. And a more recent view is that actually most of the solutions fitting the training data generalize, and gradient descent, all it does is just find one of them in a non-adversarial way. And so this basically question that arises given these two views and the conflicting evidence is, does gradient descent, is it really needed for good generalization? And we looked at this question for matrix factorization, which is a common testbed for analyzing generalization in deep learning. And we saw that even in this very, very simple setting, there is no simple answer. Okay? Gradient descent is needed if the model is wide, and it's not needed if the model is deep. Okay, so I guess the hope of there being a simple answer in general is very slim, because even if in the simplest non-trivial setting, the answer depends on the architecture of the model. Just word about future work. So we had a bunch of papers in the last couple of years that showed generalization through gradient descent, that gradient descent achieves good generalization in various settings that are much more realistic than matrix factorization. For example, in tensor factorizations, these are kind of multidimensional entities that are a lot closer to convolutional neural networks and things like that. We also showed it for different sequence-to-sequence models like structured state space models, ones that underlie LLMs, Mamba, and things like that, if you've heard. And also in reinforcement learning settings. In control settings where you run policy gradient, which means gradient descent, to learn a controller. And we showed in all these settings that gradient descent yields a generalizing solution. And usually it's under some kind of low rank assumption on the ground truth, on the real data. Okay. And something that I think would be very interesting to look at is the volume hypothesis in these settings, whether gradient descent is needed. And if we have this kind of understanding, it's not just a theoretical question. It's known that sometimes in deep learning, there's a certain trade-off, right? If you sometimes Adam converges faster than gradient descent, but generalizes worse. Different acceleration methods and things like that. And if you have this kind of understanding for when the volume hypothesis holds, then maybe you could tell in advance in which settings there's a greater risk of generalization deteriorating when you change optimizers. Okay, maybe in some, you're working with a certain setting and gradient descent gives you good generalization, okay, but it converges slowly. And then if you want to change to Adam, you'll get worse generalization. But it might be that if you change something in your setting, that something could lead the volume hypothesis to hold. And then Adam wouldn't suffer from deteriorated generalization because almost any optimizer that fits the training data will generalize. And all you need to worry about is to fit the training data quickly. Okay, so this might guide you in architectural decisions that will allow you to focus on fast optimization and not worry about deteriorated generalization. And with that, I'll conclude. So thanks.